This video is going to outline a second different method that you can use if you'd like to for example 2. And it's referred to as the resolution of forces. So depending on your background, maybe if you've taken some physics, you might already be familiar with this method, and for that reason you might like it better. So I thought I would just include it here in case anybody wants to use this method. You totally can. If you prefer the method that was shown in the first video, you can go ahead and use that and just disregard this video altogether. Okay, so what the resolution of forces idea stems from is the idea that, so if we take a look at this first string, which we called tension 1, it's kind of acting up and to the left. So if I want to resolve that vector into its component forces, if something is pulling up and to the left, then it must mean that there's some kind of force pulling to the left, and there's some kind of force pulling upwards, and the resultant force then is up and to the left. So it's like I'm going to look at this red vector and imagine it broken into two pieces, this piece and this piece, as its component pieces. So maybe let's name some things so that we know what we're talking about. So let's pretend that I call this point O, and let's call this point A and B. Okay, so that little triangle that I just created is a right angle triangle, right? And notice too that this angle, this 50-degree angle, it's not inside that triangle right now. It's outside the triangle. But since we were imagining that this was the ceiling, and you can assume that all ceilings are horizontal, and we're imagining that this is a horizontal component force, then those two lines would be parallel. And with parallel lines, if you recall, you're allowed to consider that the Z pattern tells us that the angles in the corners of a Z pattern are equal. So I can put 50 degrees in this little corner here. So I can also name, this would be vector OA, this would be vector AB, and well, I've already named that first vector the T1 vector, the tension in vector 1. So it's this vector that I'll make it clearly red again. So that's the original vector from the diagram. Okay, so I can now do the same thing with that second tension vector. So maybe I'll make that second tension vector yellow. It's pulling up and to the right. So to break it into its components, it must mean that there's a component pulling to the right and there's a second force pulling upwards, and it's the result of those two forces that creates that yellow tension vector. So again, let's name some stuff so that we know what we're talking about. So I've already named this point O. Let's name this point C and this point D. So now I can name this vector DC, and I can name this vector OD. Okay. So the next idea to follow is that in the question it said that this diagram, this system created by these forces, is in a state of equilibrium. So what does that mean then if it's in a state of equilibrium? It means, if I'm thinking about the horizontal and vertical components, it means that horizontally you have this blue force pulling to the left, and then you have this green force pulling to the right. But since it says that that weight, that 100 Newton force that's acting downwards, it's not moving, I can imagine then that the magnitude of that OA vector, that blue vector that's pulling to the left, and the magnitude of that OD vector, that green vector that's pulling to the right, the magnitudes of those two vectors must be equal to each other if the the object being held by those strings isn't moving. Similarly, vertically, if I'm also in equilibrium, it means that the forces acting upwards and the forces acting downwards must be equal to each other. So what are the forces acting upwards? I have this AB force pulling upwards, and I have this DC force pulling upwards. And what force do I have pulling downwards? Because if we're talking about vertical components, I have this 100 Newton force pulling downwards. So vertically, if I'm in equilibrium, it means that the magnitude of the two forces pulling upwards, so the magnitude of the AB vector plus the magnitude of the DC vector, those two vectors that are pulling upwards, must equal the magnitude of the vector pulling downwards. Well, what's that? The magnitude of that vector pulling downwards is 100 newtons. So because it's in a state of equilibrium, then it means that these two statements are true. Okay, so how can we use this to find the tension in rope 1 and rope 2? So let's start with the horizontal components. Okay, so this vector OA, if I wanted to actually find its magnitude, because I want to be able to set its magnitude equal to the magnitude of OD, right? But before I can do that, I need to find something to represent the magnitude of OA. So I made this little right angle triangle, right? So that means that I can use SOHCAHTOA to, put angles and sides together. So I have this 50-degree angle. I'm trying to come up with a magnitude of this OA side. And well, the other side that's involved in the question is the tension in this red vector. So then if I think about SOHCAHTOA and I say which trig ratio involves this is adjacent and this is hypotenuse, it's cos, right? So then I would say cos of 50 degrees equals, it's supposed to be adjacent. Well, adjacent would be the magnitude of the OA vector because I need the length of that side, right? Divided by the magnitude of the T1 vector, the tension in that red rope. So if I want something to represent the magnitude of OA, I can just say then, okay, so then the magnitude of OA equals the tension in rope 1, its magnitude, multiplied by cos 50. Like I just bring that denominator to the other side. So I have this, and I'm just going to keep it here for a moment. And let's jump over to the green triangle and do the same thing. In the green triangle, okay, so I don't have any angles, but I have this angle up here is 30 degrees. So Z pattern tells me that this angle inside the triangle here is also 30 degrees. So if I want to involve the OD vector along with the tension 2 vector, again I can use cos, right? So now in the green triangle, I can say that the cos of, this time it's 30 degrees, equals adjacent is the magnitude of the OD vector divided by the hypotenuse is the magnitude of the tension 2 vector. Okay, solving for the magnitude of the OD vector gives us the tension in rope 2's magnitude multiplied by cos 30. Okay, so let's put this aside. And now let's say, okay, well, what should we do with these? Well, what we should do with these is we said that the system is in a state of equilibrium. So we said that the magnitude of these two vectors must be equal to each other. So I can say, therefore, these two things must be equal to each other. Because this represents the magnitude of vector OA and this represents the magnitude of vector OB. So I can say, therefore, the magnitude of the tension 1 multiplied by cos 50 has to equal the magnitude of tension 2 multiplied by the cos of 30 degrees. So I have an equation now that is true and that has my tensions in them, but I have one equation with two unknowns, so that I can't solve yet. But that's why we have this second piece of information, which is, okay, well, now let's consider in the same way the vertical component forces that are acting on this weight. So what are the vertical component forces? It's the magnitude, it's the AB vector and the DC vector, which are both pulling upwards. And then it's that 100 Newton vector that's pulling downwards. So let's do the same idea and see, well, can I get an expression that can represent the magnitude of the AB vector? So again, I already have my triangles drawn. So using the blue triangle, this time, because I have opposite over hypotenuse, I can say that the sine of 50 degrees equals the magnitude of the AB vector over the magnitude in string 1. So the magnitude of the AB vector then can be represented by the tension in string 1 multiplied by the sine of 50 degrees. Keep this aside and do the same thing for the magnitude of the other vertical vector. So now I'm in the green triangle. I can use sine again and say that the sine of 30 degrees this time equals the magnitude of the DC vector divided by the magnitude of the tension in string 2. So the magnitude of the DC vector equals the magnitude in tension 2 times sine 30. Okay, so what am I going to do with these expressions? Because now I have an expression that represents the magnitude of the AB vector, and I have an expression that represents the magnitude of the DC vector. Well, what I'm going to do with it is plug it into this equation. The idea that since the system is in equilibrium, the sum of the magnitudes of the two vertical components that are pulling upwards is equal to the magnitude of the force pulling downwards. And what does that give me then? That gives me a second equation. The AB vector's magnitude can be represented by the magnitude of T1 times sine 50 degrees. And then it says plus, so plus the magnitude of the DC vector. So this expression represents the magnitude of the DC vector. So it's the magnitude in tension 2 times the sine of 30 degrees equals 100. So look what I have now. I have two equations with my two unknowns that I'm trying to solve for. So I have a system of equations. So how do you solve a system of equations? Substitution or elimination, right? So that's what I'm going to do now. I'm going to solve this system because what I'm trying to find is what is the magnitude of the tension 1 vector and what is the magnitude of the tension 2 vector. So I'm going to solve this one. I'm going to solve by substitution. So I'm going to take my first equation and isolate one of the variables, sub it into the second equation, and then I'll have an equation with just one unknown, and then I can go from there and solve for that first unknown and then the second. So if I call these equation 1 and 2, then from equation 1, if I solve for, it doesn't matter which variable, let's say I solve for the magnitude of the tension 1 vector, it would equal, I would have to bring cos 50 to the other side, and I would bring it to the other side with division. So I would have cos 30 times the magnitude in the tension 2 vector, all divided by, so all I'm doing is bringing the cos 50 to the other side. So now I have an expression for T1. What am I going to do with it? I'm going to sub it into equation 2. So in equation 2, in the place for this tension 1 vector, I'm going to sub in this yellow expression. So instead of putting tension 1, I'm going to put in cos 30 times the magnitude of the tension 2 vector divided by cos 50. So that's in place of T1, the magnitude of T1. Then I'm just going to copy the rest of the equation. Times sine 50 degrees plus the magnitude of tension 2 times sine 30 degrees equals 100. And see, what I have now is one equation, one unknown. So I just have to do some nice simplifying, collecting like terms, and then isolate T2. So just to make sure you understand the steps, like these are really like terms. This is two big terms and they're like terms, right? They both just have this variable magnitude of T2 in them. So how do you collect like terms? You combine their coefficients, right? In terms of scalars, those coefficients, in terms of vectors, those coefficients would be referred to as scalars. So you combine their scalars. So what numbers are being multiplied by tension 2 here? Cos 30 times sine 50 over cos 50. So that scalar, cos 30 times sine 50 divided by cos 50 is the scalar getting multiplied by T1 in that first term. And I'm supposed to add it with the scalar getting multiplied by tension 2 in the second term. So in the second term, that would be sine 30. So once I combine those scalars, that's going to become the new scalar that's multiplied by the tension in string 2. And that's equal to 100. So now, to isolate the tension in rope 2, I just do 100 divided by this big bracket, and then I just carefully plug it in on my calculator, probably using brackets, and I'll find that the tension in rope 2 comes out to be approximately 65.3 newtons. The exact same answer we got using method 1 in the first video, but just obtaining it a different way by looking at component forces. So how do I finish the question and find the magnitude in string 1? Well, I have the magnitude in string 2, right? So I go back to my equations, any equation I want, and I sub in the magnitude of string 2 so I can get the magnitude of string 1. This would be the smartest place to sub it in because this already has T1 by itself. So it equals cos 30 degrees. It's supposed to be times the magnitude of T2, which I now have, divided by cos 50 degrees, and I'll get that the magnitude in the T1 vector is 87.9 newtons approximately. Again, same answer I got using method 1, but if this way feels more comfortable to you because you're used to doing something similar to this in physics, feel free to use it. If this method feels like, why would I do this? This is so much more work than what we did in method 1, then feel free to ignore this. Your choice, okay? Resolving a force into its horizontal and vertical components. That's it.